Welcome to Atomic City, where metals throw an electron parade. Here, electrons don't belong to one atom. They're free to move everywhere, creating a sea of electrons that gives metal strength, flexibility, and great conductivity. In Atomic City, every metal shares its outer electrons. These delocalized electrons move freely like a giant crowd of charge. That's why all metals conduct. Here are some of the big players in the electricity business. Aluminium, light, strong, always ready to share. Copper, the workhorse of wires and circuits. Silver, super shiny and an excellent conductor. Gold, stable and reliable for precision contacts. Next up, we'll be looking at sodium, and we're going to watch what happens when she shares her outer electrons with her metal friends and creates the sea of delocalized electrons. So now we're going to meet part of the group 1 family, lithium, sodium and potassium. We're going to take a look at sodium in more detail. Sodium, energetic and keen to share. I share my outer electrons with my sodium friends, says sodium. That's what starts the sea. As the electron breaks free, it joins a shared sea of delocalized electrons flying around positive ions in the lattice. As you can see on the image, we have our positive ions that are fixed in place and our shared electrons that are whizzing around with no logical direction currently. Due to the electron being disattached from the ion and moving freely, it forms a positive ion, which is called a cation. We've got our cat here to symbolise that. This shared sea makes the metal strong, flexible and able to conduct electricity. So these electrons, when given voltage, will carry electricity through conductors such as copper, primarily in wires. Welcome to the Great Electron Parade. All across this metal city, the positive metal ions, standing tall like buildings, stay fixed firmly in place. They form a giant regular structure, giving this metal its strength. Now look around the streets are full of our mini electron bots. They represent the delocalized electrons, the free movers that zoom all around the metal lattice. This is what we mean when we say metal contains a sea of delocalized electrons. Okay, so you can see the little guys whizzing around all over the place, not confined to one of the metal ion bots. Each electron bot can travel anywhere inside the structure, weaving between the positive ions. Even though the ions don't move, these electrons flow freely, and that's the secret of how metals conduct electricity and heat. Mere volt keeps the system stable, making sure the metal stays connected, while the electrons do their parade lap, keeping everything alive and buzzing with energy. So remember, the positive ions stay locked in place. That's what makes metals strong and solid. The delocalized electrons move freely. That's what makes metals conduct electricity. Together they form a metallic bond, a powerful electrostatic attraction that holds the entire structure together. This glowing highway of moving electrons is why we call it sea of electrons. It's not random, it's organized, energetic, and it what gives metals their amazing properties. Here's the inside of a metal. Each atom loses its outer electrons, leaving positive ions packed together in a regular pattern. The free electrons move all round. This is called a sea of delocalized electrons. These delocalized electrons drift between the positive ions, keep the structure held tightly together because opposite charges attract. That's the metallic bond. When no voltage is applied, these electrons wander in every direction at random. There's no overall movement, no current yet. Here comes Mayor Volt, bringing the battery power. He creates the difference in electric potential, a voltage that tells the electrons which way to move. Once the voltage is applied, amps gets to work. He represents the electric current. The flow of delocalized electrons now drifting in one direction. With Mayor Volt pushing, amps running, we now have an electric current. Even though each electron moves randomly together, they drift steadily, transferring energy through the metal. So metallic bonding keeps the metal lattice strong. Mere volt provides the push and amp shows us the current flow. That's how electricity moves through metals. Why are metals such good conductors? Let's start with magnesium. Magnesium has 2 valence electrons to give to the sea of delocalised electrons. Key idea, outer shell electrons in metals are free to move. They carry charge and let metals conduct. More valence electrons usually mean stronger metallic bonds. Each Mg atom loses 2 electrons to form Mg2+. A higher positive charge means a stronger pull on the sea. Now let's take a look at aluminium. Aluminium has 3 valence electrons, all donated to the sea. More delocalised electrons can improve conductivity. Aluminium loses 3 electrons, forming Ai3+ ions. More delocalised electrons, stronger attraction between ions and electrons. That gives stronger metallic bonds, so aluminium has a higher melting point and better conductivity. Smaller Ai3+ ions pull electrons closer. The lattice is tighter and stronger. Metals are positive ions in a giant lattice with 3 delocalised electrons. The electrostatic attraction between ions and electrons is the metallic bond, giving high melting points, good electrical thermal conduction, and malleability and ductility. Stronger bonds come from more electrons, higher ion charge, or smaller ions holding electrons closer. Remember, higher voltage makes a stronger field, so electrons drift faster and current increases.